Functions are relationships that connect one or more input variables, in this example known as the value x, with only one output variable, in this case denoted with a y. This is typically expressed as y equals f of x, where x represents the independent variables or inputs, f represents the function, and y represents the dependent variable or output, as it depends on the input x. We can generalize these concepts to answer questions such as how a change in one variable impacts the value of another. Let's look at an example. Suppose we want to determine the cost of taking a cab in New York City. We know that the cost per mile is $2 and there is a base fare of $3. We want to determine the cost, the dependent variable y, based on the number of miles traveled, the independent variable x. This relationship can be represented by the equation y equals f of x, which states that the function f takes an input variable x and produces an output variable y. In this example, the function is given by 2x plus 3, where 2x represents the $2 per mile multiplied by the number of miles, and the plus $3 represents the base fare. Essentially, this function helps us understand how a change in one or more variables, such as the miles traveled, affects another variable, such as the cost. If we want to travel 4 miles, we evaluate the function with x equals to 4. We pay 2 times 4 plus 3, which equals to $11. This is known as a formula representation. Notice that the $2 per mile multiplied by the number of miles produces a dollar amount, to which we add the $3 base fare, resulting in a dollar amount for the total fare. It is important that the units on the left-hand side of the equation match the units on the right-hand side. This is useful when you are given a function and ask for an interpretation. There are also two other ways of representing these results. One way is tabular representation, where we create a table as shown here. On the left, we have a column with the independent values. All potential values that the independent variable can take are known as the domain. On the right, we have a column with the dependent variable or y values. All potential values that the dependent variable can take are known as the range. Each row in the table presents the relationship between a given independent value and its corresponding output. This is useful when we know the exact input values we will use, and in such cases, everything has been pre-calculated, making it faster for a computer to perform lookups. Another way to represent a function is graphically, where the independent variable miles is plotted on the x-axis and the dependent variable cost is plotted on the y-axis. A given xy pair can be marked on the plot as the intersection of 3 miles and $9. In this example, if we plot all the data points, they form a straight line. To summarize, we have shown 3 ways to represent functions. We can use formulas, which are useful for mathematical manipulation and gaining further insights. We can use tables, where everything is pre-calculated, so no new calculations are necessary. And finally, we can use graphs, which are good for presentation and qualitative descriptions. Here, we can see what they look like in our cab example. Frequently, analysts are tasked with empirically establishing the nature of a function, which essentially involves defining its contents. This fundamental question is addressed by the disciplines of mathematical and statistical modeling. Let's explore a few common functions. A constant function represents the simplest model. For instance, in the context of phone plans, we pay a fixed monthly fee of $50 for unlimited minutes. Regardless of whether we use 0 minutes or 1,000 minutes, the cost remains $50. This example illustrates the different inputs can yield the same output. In this case, all inputs result in exactly the same value of $50. Since there is no real relationship between the minutes used and the cost in this scenario, the amount we pay is constant regardless of phone usage. Other examples of constant functions include an all-you-can-eat buffet, where the price remains the same no matter how much food is consumed. We previously discussed a linear function using the example of estimating a cab fare. In this case, the slope m is the cost per mile and the intercept b is the base fare. Note that if the slope represented by the value m is 0, we obtain a constant function y equals b. Another common example of a linear function is the conversion of temperature from Celsius to Fahrenheit. In our previous discussion, we used x as the input and y as the output, but these characters are arbitrary and can be interchanged. For instance, in the temperature conversion example, we use C as the input, which represents the temperature in Celsius, and F as the output, which represents the temperature in Fahrenheit. Not surprisingly, functions that are not linear are classified as nonlinear. For example, a quadratic equation involves terms where one of the variables is squared, resulting in a parabolic shape. An illustration of a quadratic function could be a company determining the optimal number of chocolate chips to include in cookies based on customer satisfaction ratings that have values between 1 and 10. Where too few or too many chips yield lower satisfaction scores, and an optimal amount exists around 7 or 8 chips. It's important to note that 2 or more different inputs can have the same output value. Similarly, higher order polynomials can be used as well. Another type of function is the exponential. This can be observed in the subscriber base of a new product that gains popularity through word of mouth. The equation y equals a e to the power k times t describes such exponential growth, where a is the initial number of subscribers, k is the growth rate, and t is time. For the first few days, the growth is quite small, but in the later days, the number of subscribers increases significantly. A logarithmic function, on the other hand, models situations where a quantity grows or decays at a rate proportional to its size, but with diminishing returns. This could be seen in a marketing campaign where each dollar spent on advertising initially boosts revenue in a movie significantly, but each subsequent dollar has a smaller impact. To understand the qualitative aspect of a function described by a formula, such as whether it is increasing, decreasing, increasing at an increasing or decreasing rate, and so on, it's often helpful to plug in values and graph the function. This approach allows us to visually grasp how the function behaves under different conditions. Functions can have more than one input, but they must always yield one output. For instance, consider modeling the investment of a principal amount of $100 in a savings account, where we calculate the amount after several years with a 10% compound annual interest rate. Initially, we depict this relationship on a graph, showing the amount as a function of the years. However, we can generalize this function to include the interest rate as an additional input. This extends our model to a three-dimensional chart, where the dependent variable remains the amount of the investment and the independent variables are years and interest rate. Theoretically, the principal could also be considered an independent variable, but visualizing it would require another dimension in the graph, which is impractical. There is no theoretical limit to the number of input variables a function can accommodate. Sometimes we have functions that are linked together, meaning the output of one function becomes the input of another. For instance, let's consider a car factory example. Suppose this factory produces 10 cars per hour for 8 hours a day. Each car has a material cost of $1,000, and we want to calculate the total material cost per day. Our first function will calculate the total number of cars manufactured on a given day by multiplying 10 cars per hour times 8 hours per day, resulting in 80 cars per day. These 80 cars per day then become the input of our second function, which multiplies this number by the $1,000 cost per car. As a result, we get a final output of $80,000 in material costs per day. Functions have also been expanded into programming languages. For example, we can have a function that calculates the average of two or more numbers. In this case, it receives the input of x1 and x2 and the function adds them up and divides it by the number of inputs that it has, in this case 2, which produces the average as an output. In spreadsheet tools, we can, for example, create the variables 10, 20, and 30, use the equal average function, open the parentheses, and select the values of the range we want to calculate the average. In this case, it gives us a result of 20. Similarly, in tools like Python, we can create a list with the values of 10, 20, and 30, and then we can add them up with a function called sum, where we put in the list and divide it by the length or the number of items in that function. We can also import a library known as NumPy, and we can use np.average, where we put in our list, and this also calculates our average. And here we conclude our brief introduction to functions. If you like this video, click the like button and don't forget to subscribe for more content.